Hello, my dear students. Welcome to the 12th lecture on particle physics. And I'm going to introduce a very important and interesting topic which has got lots of applications in physics. And the topic is symmetry and its importance. Now, during these lectures, in the next 8-10 lectures, I will talk about discrete symmetry, where I will discuss parity of the particles like parity of photon, parity of leptons and baryons, neutral pions, charged pions, parity violation in weak interaction, the famous Woos experiment, then charge conjugation, C parity of photons and neutral pions, charge conjugation violation in weak interaction, different helicity of neutrino, the Goldhaber experiment, combined CP operation, K0 and K0 bar oscillation and Keon regeneration phenomena, and then CP violation in weak interactions. Then time reversal is, and how using the concept of time reversal, spin of the pion is determined. And I will also talk about in one of the classes that what will happen if there is violation of time reversal operation, how we can understand the consequence of that. Because when we are talking about CPT symmetry, and in the standard model CPT is an exact conservation law, and if CP is violated and CPT is conserved, then that means T has to be violated. Therefore, we will discuss about that. Now, symmetry in everyday life refers to a sense of harmonious and beautiful proportion and balance. Recall the famous structure of Taj Mahal, or talk about butterflies, or any symmetrical object, architecture you talk about. Therefore, sometimes we relate symmetry with beauty. In mathematics, the term has a more precise definition and is usually referred to an object that is invariant under some transformation, such as translation, reflection, rotation, or scaling. For example, rotation will give us the conservation of angular momentum. In the world of physics, symmetries are the most fundamental explanation for the way things behave, the laws of physics. For example, if I talk about gravitational law of attraction, or Coulomb's law, or talk about any other law, those were true yesterday also, they are true today, and they will be true tomorrow also. Therefore, these laws, they are independent of time. They won't depend upon your time scale. In microscopic world of physics, symmetries are linked to the actual dynamics of the system under study. For example, even if we talk about Newton's law of gravitation, then we know that no matter from which direction the particle is, whether here or here or here or here, then if the distance is same, then force will be exactly the same, and therefore that this is spherically symmetric. And every symmetry of nature yields a conservation law. In other words, every conservation law reflects an underlying symmetry. Here I have taken the example of Taj Mahal and butterfly. The left hand side is well known man-made object, and the right hand side is the natural object. Now, if I put a vertical line at the center, then what we can see that this divides these Taj Mahal into exactly two parts, or the butterfly into two parts, and they are exactly symmetric. And this is known as line symmetry. But at the same time, if I rotate Taj Mahal by 90 degree, then also it's symmetric. We won't be able to distinguish the Taj Mahal. When it was in the previous state, whether it is at 90 degree or 180 degree or 270 degree, it will be the same. And at 360, it will come back to the original place. Therefore, at some angle under rotation, this Taj Mahal is symmetric. But it's not symmetric at all angles. And that is why this rotation has discrete symmetry. While here first we are talking about line symmetry or the mirror symmetry. Therefore, this is exactly the mirror image we have from the right and left. Then if you look at this structure also, or the famous structure of Konark temple, if you hide these points, then it's difficult or impossible to distinguish this wheel if you are rotating it. If we ignore the structure of the different needles of the wheel, then architecturally symmetry of the wheel is preserved. You rotate it or you look at it, what you will see that this is completely symmetric. Now, from where this word symmetry has come? This word has come from the Greek word symmetron, meaning well proportioned, well ordered. In physics, a symmetry of a physical system is a physical or mathematical feature of the system. Either you have observed it or it is the intrinsic property of the system that is preserved or remains unchanged under some transformation. It is an operation that if one performs on a system, leaves the system invariant. That is, the system remains indistinguishable from the original one. And that is why people often equate symmetry with beauty, as I have taken the example of Taj Mahal and butterfly and all that. And the importance of symmetry in physics may be realized by the famous statement by Hermann Weyl, who was a great theorist. As far as I see, all a priori statements in physics have their origin in symmetry. Now I have taken these four basic pictures into account. The first one is of a square. The second one, this is a square, this is a star, this is an equilateral triangle, and this is an arrow. What you see that if I put a vertical line at the center, then at all the places, then the left and the right figure, they are indistinguishable. But if I rotate this square by some angle other than 90, 180 and 270, then there will be no symmetry in it. Similarly, this star will be symmetric under rotation if I rotate it by 72 degrees. Other than that, it will be distinguishable. This equilateral triangle, line symmetry is there, but if I rotate it by 120 degree, then either in the clockwise direction or anti-clockwise direction, then we won't be able to distinguish it. That means it will be indistinguishable. Not only 120, if I rotate by 240 degree in the clockwise direction, which will be equivalent to 120 degree in the anti-clockwise direction, this equilateral triangle is indistinguishable. But when we talk about this arrow, then except for 360 degree, this arrow is distinguishable under rotation. Therefore, if we talk about these objects are symmetric under rotation at certain angles, but not at all the angles. Therefore, they have discrete symmetry. Okay? While if you talk about a sphere, like rotation of a earth, that is continuous. Now let me take some simple examples before we delve in great detail. Like we have a circle and we are talking, like I'm talking about a bicycle where we have spokes like this, and they are equally spaced, equal at length, and it is just moving like this. Then we won't be able to distinguish whether this spoke is here or the other spoke is here. It will be indistinguishable. Therefore, when we are talking about the movement of this wheel on the road, then we are unable to tell that which spoke is on what side. And this is nothing but the translational symmetry. Then, in the case of circle, there is also rotational symmetry. Then, in the case of circle, if I put a dashed line just at the center, then it has reflection symmetry also. Therefore, mind it, in the case of circle, we are talking about the first case, translational symmetry. Then, in the second case, we are talking about rotational symmetry. Then in the third case, we are talking about reflection symmetry. Then we have a line symmetry also, which is n-fold. Therefore, just we have n-fold line symmetry if we are talking about a circle. Therefore, a circle has many symmetries: rotational, reflection, line, and as well as translational symmetry. Now, in comparison to that, if I take a square, then what we say that this has, and put a vertical dashed line either at this center as the vertical line or at the center as the horizontal line, then we come across the translational symmetry. Then rotation by angle other than 180 degree. For example, if this is a parallelogram, makes or destroys the symmetry of a rectangle, while in the case of a square, rotation by 90 degree keeps the symmetry. In the case of parallelogram, rotation by 180 degree keeps the symmetry. Other than that, symmetry is destroyed. Then we have translational symmetry as well as we have the diagonal symmetry. If we talk about the equilateral triangle, we have reflection symmetry, we have line symmetry, rotation by 120 degree leaves the object invariant, we won't be able to distinguish it. Then we have translational symmetry, and isosceles triangle has two-fold line symmetry while scalene triangle has none. Then the square which we have talked about, this has reflection symmetry, line symmetry which is fourfold, rotation by 90 degrees, translational symmetry as well as the diagonal symmetry. Therefore, you can see that an object can have various symmetries, or it can be invariant under reflection, under translation and rotation, etc. Then now let us talk about symmetry breaking in geometrical objects. Suppose I am talking about a cycle which has got equally spaced spokes, and we have the center of this cycle where we have a steel ball at the center. Now, if this is rotating, then what I have told you that during translation, we won't be able to make any distinction. It will be indistinguishable, or that means unchanged under all the different symmetry transformations which we have discussed earlier. But as I will move this steel ball on any of this side, like here, and then talk about rotation, then we see that the symmetry has gone. Okay, therefore the important point is the symmetry which was earlier there when this steel ball was at the center, as we have moved this ball to, at some other point, the symmetry has gone. Similarly, you can see that if there is a field where lots of grasses are there, and there is a horse who wants to graze this field. Now, as long as he has not started grazing the field, symmetry is there. But as he has started, chooses right hand side to graze the field or the left hand side to graze the field, symmetry has broken. Now, similarly to that, we can take another example. Suppose there is a round dining table where there are various chairs placed, and on the table you have spoon and forks. Spoon and forks. Now, if all the 6 people are sitting over here, yet they have not started eating, then all these are symmetric. But as soon as the very first person has picked either a fork or a spoon, then symmetry is broken. Therefore, symmetry was there but has got broken when the horse has started grazing the field, or symmetry was there but once a person has picked a spoon or a fork from the right hand side, then symmetry has vanished. Or from the left hand side, if he has started to pick the fork, then symmetry has gone. Now, symmetry is a foundational concept in physics, serving as a guiding principle that unveils deep insights into the fundamental laws governing the universe. In the context of physics, symmetry refers to the invariance of physical laws under specific transformations, revealing underlying order and coherence in the natural world. One of the most profound manifestations of symmetry is found in Noether's theorem, formulated by mathematician Emil Noether, which says that, or which connects symmetry and the conservation laws. It states that to every continuous symmetry of a Lagrangian, there is a quantity which is conserved by its dynamics. Therefore, this is a very famous theorem that to every continuous symmetry, there is a conservation law. Translational symmetry, which implies that the laws of physics remain unchanged when one shifts the entire system in space, underlies the conservation of energy through the work energy theorem. As I have told you that laws of physics will be the same for all time, and this invariance or independence in space-time underlies the conservation of energy. Then we have talked about time symmetry, where we had the invariance of physical laws under time translation. This is what we call as the conservation of energy through Noether's theorem. Symmetry is also central to the standard model of particle physics. For example, the gauge symmetries in the theoretical framework govern the fundamental forces: electromagnetic, weak, nuclear, and strong nuclear forces. So therefore, for example, invariance of electrodynamics under gauge transformation leads to conservation of charge. The electromagnetic force, for instance, is described by the theory of electromagnetism, which exhibits symmetry under transformation of electromagnetic gauge group. Then we have global symmetry as well as local symmetry. For example, in the case of global symmetry, it holds at all points, while local symmetry varies from point to point. As you can see in the second picture of this, where we have a sphere, if we rotate it, then it is indistinguishable at all points when you are rotating it. But if you are talking about such a and you are rotating it, then as you can see that it's not symmetric. As you rotate, it is moving in some way at some point and another way at another points, and here it is not symmetric. Therefore we have local symmetry as well as we have global symmetry, while we have a continuous symmetry in the case of the rotation of earth, and continuous symmetry is an example of a space-time symmetry, and this is achieved by the infinitesimal transformations. Therefore you can achieve continuous symmetry with the help of infinitesimal transformation, while the discrete symmetry you cannot achieve with the help of infinitesimal transformation. Now the example of broken or hidden symmetry, for example, if I have taken a Mexican hat and I have put a ball at the top of the hat, as we know that this is not the stable point. The stable point will be the point of minimum potential energy, and that will be some place on this at the bottom of this Mexican hat. But if we look at it, then it is a symmetrical object. We are rotating it, then it is a symmetrical object. But very soon this ball is going to come to the ground state, and the ground state is not symmetric, because once it chooses either to come to the left side direction or the right hand side direction, or in fact it has got n number of ways to lie on this bottom of the Mexican curve, as soon as it chooses one place, the symmetry is broken. Therefore the ground state is not symmetric, but the higher states are symmetric in nature. Then we have the discrete symmetries, like we have shown that if we take a square, then under rotation by 90 degree, it is indistinguishable. But if we make this change by any other angle, then it is not distinguishable. If you make it the change by at any other angle, you will be able to distinguish it. Therefore, if you do it by 90 degree or 180 degree or 270 degree, then it is fine. But for this square, if you choose any other angle, then this square will be distinguishable. And that is why we are calling this the choice of the different angles where this square is symmetric as the discrete symmetry. Then we have a very important concept in supersymmetry, though I am not going to discuss it. It relates elementary standard model particles with corresponding bosons. It says that as many fermions you have also the equal number of bosons in nature. Like for gluons, we have gluino. For electron, we have electrolino. S leptons, or you call it by a neutrino, you are call it by the name neutralino. Therefore this concept is also there, which is known as supersymmetric model. Then we have the gauge symmetry, which I have talked about, and this is an internal symmetry. For example, invariance of electrodynamics under gauge transformation that leads to the conservation of charge. Similarly, we have the conservation of lepton number, baryon number, etc. Then when we talk about continuous symmetry, what I have told you, like rotation of earth, this is performed by infinitesimal transformation, and the important point is that of Noether's theorem, which says us that each continuous symmetry is associated with the conservation of a physical quantity. Like translation in time leads to conservation of energy, translation in space leads to conservation of linear momenta, invariance rotation in space leads to conservation of angular momentum. Therefore, to each continuous symmetry, there is an associated conservation law. We have conservation of energy, linear momentum, angular momentum, etc., etc. For example, if we talk about conservation of energy, and this is a person who is moving along this mountain top, then what we find out that the total energy of the system will remain conserved. And as it is moving up, the total energy is invariant. Therefore, translation in time symmetry, or the invariance of physical laws under time translation, is associated with the conservation of energy throughout the motion of this cyclist on this path. And this is the consequence of Noether's theorem. Similarly, when we talk about conservation of linear momenta, where the symmetry of a physical system under translational invariance leads to the conservation of linear momentum, while rotational symmetry results in the conservation of angular momentum. I have just shown here billiard balls, and you know that how does this conservation of linear momentum takes place. This we have already discussed in one of the classes. Then when we talk about the conservation of angular momentum, then a girl who is skating on an ice and her hands are spread, then the angular momentum is fixed. Now when her hands are stretched, she has got some moment of inertia and rotating. She is rotating with some angular velocity omega. But as she squeezes her hand towards the body, then what happens? Her angular velocity increases, and that way the angular momentum is conserved. Therefore, either you have a large moment of inertia and a small angular velocity, or you have a small moment of inertia and large angular velocity. But the end point is that in both the cases, angular momentum will remain conserved. Now, in our next class, we shall start discussing about the discrete symmetry. There I will first start with the well-known example of discrete symmetry, that is the parity operation and its consequence in particularly in weak interaction physics, and how we determine the parity of mesons, and why not we can determine the parity of leptons and baryons. Stay tuned. See you in the next class. Thank you very much.